A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Herman, I was thinking about this while we were walking through the old city yesterday. We live in a place where history feels like it is layered in stone, right? Thousands of years of events just sitting on top of each other. But most of us go through our day with this very rigid, very flat idea of how time and space actually work. We think a second is a second, and a meter is a meter, no matter where you are or how fast you are moving. It is the ultimate common sense. But common sense is often just a collection of prejudices we have acquired by the age of 18.
Herman Poppleberry here, and you are hitting on the fundamental illusion of human perception, corn. We live in what physicists call a Newtonian world in our daily lives. Isaac Newton gave us these beautiful, predictable laws where time is like an arrow shot from a bow, moving at a constant speed for everyone, everywhere. It is comfortable, it makes sense, it allows us to build bridges and bake cakes. But it is also, strictly speaking, wrong. It is an approximation that only works because we move so slowly compared to the speed of light.
And that is what our housemate Daniel was getting at with the prompt he sent us this week. He was asking if we could break down relativity in a way that actually makes sense for a normal person. Not just the math, which most people tune out immediately, but why it matters. Because there is this weird gap. People love to quote Albert Einstein. They love the hair and the formula, E=mc². But if you ask them why their phone can tell them they are standing on the corner of Jaffa Street instead of a block away in the middle of a wall, they have no idea that Einstein is the reason that works. They think it is just satellite magic.
It is the ultimate dinner party trap. You want to sound smart, so you mention relativity, but then someone asks a follow-up question and you realize you have no idea how space can be curved. It sounds like science fiction. But as we have talked about in past episodes, specifically back in episode 5086 when we looked at high-precision timekeeping, the universe does not care about our intuition. It operates on a set of rules that are much more flexible and, frankly, much weirder than we imagine. If you do not account for these rules, the modern world literally stops functioning. Your Uber driver would never find your house. Your bank transactions would fail. The power grid would desynchronize.
So today we are going to strip away the complex equations and look at the actual architecture of reality. We are going to look at why the speed of light is the universal speed limit, how gravity literally stretches time like a piece of taffy, and how the engineers who built the global positioning system had to account for these ghostly effects just to make sure your food delivery shows up at the right door. We want to give Daniel, and all of you, the tools to not just name-drop Einstein, but to actually explain how his brain changed the way we navigate the planet.
I love this topic because it is the perfect example of how pure science eventually becomes essential infrastructure. You cannot have a modern high-tech economy without accounting for the fact that time is not a constant. It is a variable.
Let's start with the basics then. When people say relativity, they're usually talking about two different things that Einstein came up with. There is special relativity and general relativity. Herman, if you were at that dinner party Daniel mentioned, how do you distinguish between the two in 30 seconds?
Okay, here is the elevator pitch. Special relativity, which Einstein published in 1905, is about speed and how it affects time and space for people moving at different velocities. It says the laws of physics are the same for everyone, but the speed of light is the absolute limit that never changes. General relativity, which came about a decade later in 1915, is about gravity. It says that gravity isn't a force, pulling on things like a magnet, but rather a curvature in the fabric of space and time itself. Mass tells space how to curve, and space tells mass how to move.
Okay, let's unpack that first part because the speed of light is constant. Thing is where everyone usually gets tripped up. In our normal world, if I am on a train moving at 50 kilometers per hour and I throw a ball forward at 10 kilometers per hour, a person standing on the track sees that ball moving at 60 kilometers per hour. Speeds add up. That is intuitive. It is what we call Galilean relativity.
Right, and that works perfectly for trains and balls. But it does not work for light. This is the big discovery. Imagine you are on a spaceship moving at 99% the speed of light. You turn on a flashlight. You see the light moving away from you at exactly 299,792,458 meters per second. Now, a person standing still on a nearby planet watches you fly by. You might think they would see the light moving at nearly twice the speed of light because the ship is already moving so fast. But they don't. They see the light moving at exactly the same speed you do. 299,792,458 meters per second, not a meter faster.
And that is the special part. To keep the speed of light exactly the same for both people, something else has to give. If the speed is distance divided by time, and the speed cannot change, then the distance and the time must change relative to the person watching. It is like the universe has a built-in governor that forces time to slow down and space to contract, just to protect the speed of light.
This leads to what we call time dilation. If you are moving very fast relative to me, I will look at your clock and see it ticking slower than mine. To you, everything feels normal. Your heart beats normally, your watch ticks normally. But from my perspective, you're moving through time in slow motion. This isn't an optical illusion, it is a physical reality. We see this with subatomic particles called muons. These particles are created in the upper atmosphere by cosmic rays. They are very unstable and should decay in about 2 microseconds. Even moving near the speed of light, they shouldn't have enough time to reach the ground, but they do. Why? Because from our perspective, their internal clocks are running so slowly that they live long enough to hit our detectors on the surface.
I remember we touched on this in episode 734 when we talked about the chaos of time standards. It feels like a philosophical point until you realize it is a physical reality. There was that famous experiment in 1971, the Hofflake-Keating experiment. They literally took 4 atomic clocks, put them on commercial airliners, and flew them around the world.
That is one of my favorite simple proofs. They flew one set of clocks eastward, one set westward, and kept one set on the ground at the United States Naval Observatory. Now remember, commercial jets are fast, but they are not speed of light, fast. We are talking about tiny, tiny fractions of a second. But when the planes landed and they compared the clocks, the ones that had been moving were younger or older, depending on the direction. The eastward bound clocks, which were moving faster relative to the center of the Earth because of the Earth's rotation, lost time compared to the ground clocks.
It was nanoseconds, right? Something like 50 or 60 nanoseconds difference. It sounds like nothing, but for an atomic clock that is accurate to a billionth of a second, 50 nanoseconds is a massive measurable gap.
Precisely. It was exactly what Einstein's math predicted. It proved that time is not a universal background hum. It is a personal experience tied to your velocity. But here is where it gets even more interesting and moves into general relativity. Those clocks on the planes were also affected by gravity because they were higher up in the atmosphere, further away from the center of the Earth.
Right, so that brings us to the second pillar, general relativity. If special relativity says speed slows down time, general relativity says gravity also affects time, but it does it in a way that feels even more like science fiction.
Well, think of space-time as a fabric, like a giant trampoline. If you put a bowling ball in the middle of that trampoline, it creates a dip. It curves the fabric. If you roll a marble nearby, it doesn't move in a straight line because it wants to. It follows the curve of the dip. That is what gravity is. It is not an invisible rope pulling the marble, it is the marble following the geometry of the floor. But here is the kicker, it is not just space that is curving, it is space-time. They are linked. When the fabric of space is stretched by a massive object like the Earth, the intervals of time are also stretched. The closer you are to a massive object, the deeper you are in that gravity well, the slower time passes.
This is the part that always blows my mind. If I live in a basement apartment in Jerusalem and you live in a penthouse at the top of a skyscraper, I am technically aging slower than you because I am closer to the center of the Earth's mass. I am deeper in the dent of the trampoline.
You are, though the difference is so small, it would take billions of years for it to add up to anything a human would notice. But for high-precision electronics, it is a massive problem. And this is where we get to the GPS satellites, which is the best practical answer for Daniel's prompt. This is the why should I care moment for the dinner party.
Let's really dive into the GPS thing because I think people take for granted how insane that technology is. There are about 30 satellites orbiting the Earth at any given time. They are about 20,000 kilometers up, and all they are doing, essentially, is screaming the time at us.
That is a great way to put it. A GPS satellite is basically just a very expensive, very accurate atomic clock with a radio attached to it. It sends out a signal that says it is exactly 12 o'clock, 0 minutes, and 0.000001 seconds, and here is exactly where I am located. Your phone receives that signal from at least 4 different satellites at once. It calculates how long it took for each signal to reach you, traveling at the speed of light, and because it knows the speed of light, it can figure out exactly how far away you are from each satellite. Where those spheres of distance intersect, that is where you are.
But here is the catch. For that math to work, the time on the satellite and the time on your phone have to be perfectly synchronized. If the satellite's clock is off by even a tiny fraction, the distance calculation is wrong. And because light travels so fast, nearly 300 million meters per second, even a tiny error in time translates to a massive error in distance on the ground.
Right. If the clock is off by just 1 microsecond, that is 1/1,000,000th of a second, the GPS position will be off by 300 meters, that is 3 football fields. If the error accumulates for a whole day, your GPS would be off by kilometers. It would be completely useless for navigation. You would be trying to find a coffee shop in Jerusalem, and your phone would tell you that you are in the middle of the Dead Sea.
And this is where Einstein comes in to save the day, because those satellites are being hit by both special and general relativity at the same time, and they are pulling the clock in different directions. It is a relativistic tug of war.
First, let's look at special relativity. The satellites are moving fast. They are orbiting the Earth at about 14,000 kilometers per hour. Because they are moving so much faster than we are on the ground, special relativity says their clocks should tick slower relative to us. The math tells us they lose about 7 microseconds per day because of their speed.
Okay, so they are losing 7 microseconds because they are speeding. But then you have general relativity, the gravity part.
Right, they are 20,000 kilometers up. Gravity is much weaker up there than it is down here on the surface. Because they are further out of the Earth's gravity well, time for them passes faster than it does for us. And the effect of gravity is actually much stronger than the effect of speed in this case. General relativity says those satellite clocks gain about 45 microseconds per day because they are in weaker gravity.
So we have a tug of war. We lose 7 microseconds from speed, but we gain 45 microseconds from gravity.
You do the math. 45 minus 7 gives you a net gain of 38 microseconds per day. The clocks on those satellites are literally moving into the future faster than we are. 38 microseconds sounds like nothing, but if the engineers didn't account for that, the GPS system would accumulate an error of about 10 kilometers every single day. Within a week, the system would be so far off that the entire global logistics network would collapse.
That is the aha moment. Every single time you open a map on your phone is essentially solving Einstein's field equations. The engineers actually have to offset the frequency of the atomic clocks on the satellites before they even launch them. They tune them to tick slightly slower on the ground, at 10.229999543 megahertz instead of 10.23 megahertz, so that once they get into orbit and the relativistic effects kick in, they tick at exactly the same rate as the clocks on Earth.
It is a beautiful piece of preemptive engineering. They literally built the error into the hardware because they knew the universe would correct it once it reached orbit. And this isn't just a theoretical guess. When the first GPS satellites were launched in the late 70s, there were actually some people in the military who were skeptical. They weren't sure the relativistic effects would be exactly what Einstein predicted. So they launched the first satellite with a frequency synthesizer that could be turned on or off. They ran it for a while without the correction, saw that the clock drifted exactly as predicted, and then turned the Einstein switch on. It worked perfectly. It is one of the most robust experimental verifications of relativity we have.
I think that is a powerful point for the dinner party crowd. This isn't just academic what-if stuff. This is engineering at its finest. taking these wild, abstract concepts from a physicist and turning them into a global utility that runs our entire modern world. From banking transactions, which rely on GPS timestamping to prevent fraud and ensure the order of trades, to the power grid, which uses these clocks to keep the alternating current in perfect phase across thousands of miles.
And it goes beyond just GPS. We are seeing this now in deep space exploration. If we want to land a rover on Mars with precision, we have to account for the fact that Mars has a different mass than Earth, so time moves at a different rate there. If we didn't use relativity, our navigation systems for interplanetary travel would be like trying to hit a moving target while wearing a blindfold. Even the Deep Space Network, the giant antennas we use to talk to Voyager and the James Webb Telescope, has to account for the fact that the Earth is rotating and moving in its orbit, which changes the relative velocity and thus the timing of the signals.
It really changes how you think about now, doesn't it? We talked about this in episode 734, The Illusion of Now. If time is ticking at different rates depending on where you are and how fast you are going, then there is no single universal moment that we all share. Now is a local phenomenon. There is no master clock for the universe.
It is a radical shift in worldview. Newton thought of time as the stage on which the play of the universe happens. The stage is solid and unchanging. But Einstein showed us that the stage is actually part of the play. It interacts with the actors. It bends, it stretches, it reacts to the mass and energy of the things within it. It is more like a waterbed than a wooden stage.
Let's talk about the why for a second, because I think this helps with the sounding smart goal Daniel mentioned. Why does gravity curve space? Why does mass do that? I have always liked the analogy of the fabric, but is there a deeper way to think about it for someone who wants to understand the mechanism?
It is hard to visualize because we are three-dimensional creatures trying to imagine four-dimensional geometry. But think about it this way. Mass and energy are essentially the same thing. That is, the E equals mc squared part. When you have a high concentration of energy in one place, like a planet or a star, it puts a strain on the vacuum of space.
Like a heavy weight on a piece of foam.
And the shortest distance between 2 points is no longer a straight line in our eyes. It is a curve along that strained surface. Light, which always takes the quickest path, follows that curve. We have seen this during solar eclipses. Astronomers have looked at stars that should be hidden behind the sun, but because the sun's mass curves the space around it, the starlight bends around the sun and reaches our telescopes. We see the star in a position where it shouldn't be.
That was the 1919 eclipse expedition by Arthur Eddington. That was the moment Einstein became a global celebrity. Before that, he was just a physicist with some weird ideas. After that, he was the man who proved the light bends. It was front-page news all over the world. Lights all askew in the heavens, the New York Times headline said.
And it is a great example of how science should work. You make a bold, counterintuitive prediction, and then you wait for nature to either confirm it or blow it up. Relativity has been tested thousands of times in the last century, and every single time it has held up. Even the most extreme cases, like black holes where gravity is so strong that time essentially stops, or the gravitational waves we are now detecting from colliding stars, they all fit the math. We recently detected frame dragging, the idea that a rotating mass like the Earth actually drags space-time around with it like a spoon spinning in honey. We measured it with satellites, and Einstein was right again.
So, if you are at a dinner party and you want to summarize the practical side of this for Daniel, what are the 3 key takeaways?
First, tell them that time is a physical dimension, not a constant. It is elastic. If you move fast, your time stretches. If you are near something heavy, your time stretches. It is not just a feeling, it is a measurable physical change. Second, mention the GPS correction. Without Einstein's math, your phone's GPS would fail by 10 kilometers every single day. That is the ultimate real-world application. It is the difference between finding your destination and being lost in a different city. And third, explain that gravity isn't a pull but a dent. We aren't being pulled down to the Earth, we are just rolling into the curve that the Earth's mass creates in the universe. We are literally living in a warped reality.
I like that. It moves the conversation away from scary math and toward the shape of the world. It is about geometry, really. We live in a curved universe. And that curvature is what allows us to have things like stable orbits for our satellites, and a consistent way to measure time across the globe.
And it is a universe that requires incredible precision to navigate. Think about the level of trust we put in these systems. When an autonomous vehicle or a drone is navigating through a city, it is relying on relativistic corrections to stay in its lane. We have built a civilization that is literally synchronized to the heartbeat of the cosmos, as we discussed in episode 586. We are no longer just living on Earth, we are operating in space-time.
It also makes you realize how fragile it all is. If the satellites were to lose that synchronization, or if we had a massive solar flare that disrupted those atomic clocks, our entire logistics and financial system would start to drift. We are tethered to these invisible relativistic threads. It is a testament to human ingenuity that we can even measure these things, let alone build a global utility around them.
That is why I find it so fascinating that people still argue that science is just a theory. When a theory allows you to predict the drift of a clock 20,000 kilometers in space to the nanosecond, and then you use that prediction to build a multi-trillion-dollar industry, it is more than just a theory. It is a fundamental truth about how the universe is put together. It is about recognizing the complexity of the design.
It is not just a simple clockwork mechanism. It is a living, breathing fabric. And I think that is a very humble way to look at it, actually. It is about having humility in the face of a reality that is far more complex than our common sense would suggest. We shouldn't assume that just because we perceive the world as flat and linear, it actually is. Our senses are evolved to help us find fruit and avoid predators, not to perceive the curvature of space-time.
True wisdom is acknowledging that our senses only show us a tiny slice of the spectrum. Relativity is the tool that lets us peek behind the curtain. It shows us the gears of the universe.
So, what is the next frontier? We have special relativity and general relativity. They work perfectly for big things, planets, satellites, galaxies, but they don't play well with the very small things, right? The quantum world?
That is the holy grail of physics right now. Relativity describes the universe as a smooth, continuous fabric, but quantum mechanics says the universe is grainy or pixelated at the smallest levels. When you try to combine the two, the math breaks. We get infinities that don't make sense. We are still looking for that theory of everything or quantum gravity that can bridge the gap between the curve of a galaxy and the vibration of a subatomic particle.
It is almost like we have two different operating systems for the universe, and they aren't compatible. One runs the macro, one runs the micro, and they crash when they meet at the center of a black hole.
Precisely, and that is why this is still so exciting. We aren't at the end of physics, we are just at the end of the first chapter. Understanding relativity is the baseline for anyone who wants to understand where we are going next, whether that is quantum computing, deep space colonization, or even the possibility that our reality is more of a simulation than we think, which is a topic we are going to dive into very soon.
I'm glad you brought that up. Our next episode is actually going to lean into that simulation idea. Episode 1023, The Cosmic Petri Dish. It is going to look at the laboratory hypothesis and whether the weirdness of things like relativity, the fact that there is a hard-coded speed limit for light, is actually a sign of a programmed reality.
It sounds wild, but when you look at how mathematical the universe is, how things like the speed of light act as a universal constant that everything else must bend to accommodate, it does start to look a bit like software constraints, doesn't it? If you were coding a universe, you would need a maximum processing speed.
It definitely does. But for today, I think we've given Daniel and our listeners plenty of ammunition for their next social gathering. You don't need to be a physicist to appreciate that we are all time travelers, moving through a curved landscape at different speeds. The next time you look at your phone to see where you are, just remember that you are looking at a direct confirmation of the most mind-bending theory in human history.
And if you are enjoying these deep dives into the weird side of reality, we would really appreciate it if you could leave us a review on your podcast app or on Spotify. It genuinely helps the show grow and helps other curious minds find us. We are trying to build a community of people who aren't afraid to ask the big, weird questions.
Yeah, it makes a huge difference. We love seeing the community grow. You can find all our past episodes, including the ones we mentioned today about timekeeping and the illusion of now, at myweirdprompts.com. There is a contact form there too, if you want to send us a prompt like Daniel did. We read every single one of them.
We are always looking for new rabbit holes to go down. This has been My Weird Prompts. I'm Herman Poppleberry.
And I'm Corn. Thanks for listening, and we will talk to you in the next one.
Shalom from Jerusalem.
Shalom. Shalom.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, my